Just quicker introduction to ourselves to recap. So I'm Phil Crawford. I'm a Principal Flood Risk Management Specialist at Jacobs, and I'm the technical lead for the RUA Supplementary Guidance Project from a Jacobs perspective. I'm presenting with Louise. I'll let Louise, you introduce yourself.
Yeah, good afternoon, everyone. I am Louise Glover. I work for the Environment Agency in the Evidence and Risk National Team. I've got over 20 years experience in the field of mapping and modelling, and I've been a modelling technical lead for many appraisal projects. For this project, I was the technical lead and the project manager for the Environment Agency.
Thanks, Louise. And firstly, thank you very much, everyone, for attending. We're really excited to be here speaking to you about residual uncertainty analysis, and I really do hope that you get something from this presentation and hopefully feel a little bit more informed about RUA and a little bit more confident in its application. Before we get started, I suppose, why are we talking about residual uncertainty analysis today? Two real reasons. The first of which, I think, as modelers and flood risk management professionals, it's really important that we understand the uncertainty that exists in our modelled outputs. And secondly, residual uncertainty analysis is mandatory for all flood risk management schemes in England. And so it's really important that we get to grips with it soon and we as a community become consistent in the application of it. We are jumping straight into it quite shortly. And just sort of caveat this presentation, we are following on from other presentations that we've given. If you want additional information on RUA, there's an excellent presentation by Adam Parks that is on the Flood Modeller website. I'd refer you to that. And in addition to that, I'd also encourage you to look at the original 2017 RUA guidance, but also the supplementary guidance that was released earlier this year if you've not looked at that. So what are we going to cover over the course of the next sort of 35 minutes or so? Well, I'm going to give a brief introduction to what residual uncertainty analysis is at a relatively high level. Louise is then going to cover a little bit about the supplementary guidance project itself and some of the project deliverables from that. And then I'm going to walk you through application of RUA for one of the case studies that are provided as part of that supplementary guidance, and then touch upon how Flood Modeller maybe can support you with application of RUA. And then finally, Louise is going to wrap up with some reflections from this supplementary guidance project, and we'll hopefully then have about 10 minutes for questions and answer. As Alice has already said, if you do have a question, please do drop it in the chat and we'll try and get around to answering it at the end of this webinar. So without further ado then, what is residual uncertainty analysis? Well, I think probably the first place to start before we get ahead of ourselves is what is residual uncertainty. I would say that the majority of people on this call are either hydraulic modelers or using hydraulic models and their outputs from them for a variety of purposes. And it's important that we recognize that these models are just representations of the physical environment, and therefore there isn't always going to be uncertainty associated with our outputs. There's inherently uncertainty in these models. And that uncertainty comes from the input parameters. So there's uncertainty associated with each of these parameters. For example, uncertainty associated with our choice of a weir coefficient, or potentially uncertainty in our floodplain elevation that's come from LiDAR. And it's really all of these uncertainties that combine that lead to an overall uncertainty in our modelled outputs, for example, water level. And it's really this that we refer to as the residual uncertainty. It's that remaining uncertainty in our models, and it's this that we need to be aware of. If for argument's sake we just think about using a hydraulic model for scheme design and maybe derivation of the 1% AEP design water level, then we know that these models have uncertainty associated with them. We can probably say that the model gives us the best estimate of that. For the tier 1 and tier 1.5 approaches to RUA, there's an assumption, potentially a limitation, but assumption that uncertainty in those model outputs is normally distributed. What this means in practice is there's a 50% chance that the actual 1% AEP water level is below our best estimate and 50% chance that it's above. And again, it's this really that we need to be aware of when we're thinking about residual uncertainty analysis, but more so thinking about how we manage the risk associated with that uncertainty. So what is residual uncertainty assessment? Well, I think if we start by just focusing on the assessment element of this first, the assessment is really just the quantification of the magnitude of that uncertainty. But there's more to residual uncertainty assessment than just the quantification, and a really good framework was included in the original 2017 guidance, and it's what's included on this screen. And we're encouraged to first identify the sources to that uncertainty that exist in our models, to quantify them using one of the provided methods. And in the original guidance, there was the Tier 1 and Tier 2 approach, and in the supplementary guidance, we've introduced an enhanced method called Tier 1.5. And then we're encouraged to respond to that uncertainty. Historically, I think it's probably fair to say we've responded to uncertainty through just the addition of freeboard topping up our defences. But the original guidance really encourages us to look for alternative ways to respond to that uncertainty. Let's try and reduce that uncertainty where possible. So it might be that we go and try and collect additional data to reduce uncertainty in our hydrological estimates, which in turn reduces the uncertainty in our modelled outputs. If there's one thing that you take from this presentation, I really would like it to be the importance of identifying and ideally quantifying those uncertainties early in projects, because if we don't identify them now, it's often there's insufficient time to be able to respond to those uncertainties, and the only response that's possible is that addition of freeboard or a top of the defences. So please do take that away, and please do start thinking about those uncertainties now rather than before it's too late. So before moving on and handing to Louise, I just want to maybe give a quick note on confidence intervals. I don't want to get into the details here, but confidence intervals are important for residual uncertainty analysis. We essentially calculate an RUA magnitude for a confidence interval of interest, or for a range of confidence intervals. As I've mentioned, for Tier 1 and Tier 1.5 methods of RUA, which should note are the ones that are most commonly applied in the UK at the moment, there's this assumption that the uncertainty is normally distributed, and that our best estimate is essentially the mean. It's the centre of that distribution. And as I've mentioned, in reality, there's a 50% chance that the actual, let's say 1% AEP water level, if that's what we're trying to estimate, exceeds our best estimate if you make no accounting for uncertainty. As you start to account for that uncertainty, and let's say the one standard deviation of error, we start to move towards the right-hand side of that distribution curve, and we start to reduce the chance that our new level is exceeded. So if we account for one standard deviation of error, we actually reduce the chance of exceedance to just 16%. And you can imagine as we start to account for more and more uncertainty, we reduce that chance of exceedance further. So again, it's just a quick note, but something to be aware of, because you will do, when you start to deal with residual uncertainty analysis, you will need to make a decision as to what levels of confidence you're wanting to take forward into your scheme. And with that, I'll pass to Louise, and she's going to give a few notes on supplementary guidance.
Thank you, Phil. So as an introduction to the guidance, I thought I'd just kind of give an overview of why we decided to create this. And the first key point, this does not replace the 2017 accounting for residual uncertainty guidance. The document is still the overarching guidance covering the principles and methods of residual uncertainty analysis. However, we felt that we needed to build on this to make RUA a clearer process for project teams. We're looking to create clearer standards for RUA and an understanding of what outputs are required, hopefully making the approach more consistent and easier to audit and assure. We wanted a better understanding of the who and the what in terms of creating an assessment and what role the project team had to play. And our final objective was to make the case studies clearer to follow and based on real life scenarios so that they're relatable. So what did the project deliver? So firstly, we have the supplementary guidance itself, which we'll take a closer look over the next few slides. This provides a wealth of information on undertaking an assessment, but also highlighting some of the challenges of RUA. We've also produced 5 standalone case studies for the project, covering different scheme types and environments, each one taking you through a step-by-step process of completing the RUA. These case studies are based on real projects, but have been anonymised in the reporting and can also be used as a pro forma for your own assessments, giving clarity in reporting. And finally, the package includes the RUA tool. This spreadsheet-based tool will assist in undertaking some of the calculations and providing spatially variable freeboard allowances. So over the next 3 slides, we'll take a look at the supplementary guidance document, highlighting what it contains and the sections and information we've added to support RUA. So residual uncertainty assessment is a requirement for all new appraisal projects and aligns with wider policy and guidance requiring residual uncertainty to be considered within projects. These include HM Treasury's Green Book, DEFRA's appraisal guidance, and the EA's technical guidance for appraisal. Whilst this supplementary guidance has been developed by the EA and applies to England only, we invited our partners from SEPA and Natural Resources Wales to join the conversation, alongside several of our framework suppliers, with a view that this approach can be supported across the industry and more widely across the UK. The 2017 guidance introduces 3 methods for undertaking residual uncertainty assessments, and this guidance focuses on Tier 1 application. The Tier 1 method assumes a linear relationship between variables, which rarely occurs in reality. And as Phil mentioned, practitioners across the industry have developed an enhanced methodology that we term in this guidance as Tier 1.5. This enhanced method addresses some of the limitations of the linear approach, and through limited additional sensitivity analysis of the variables provides a far more robust solution. The Tier 1.5 methodology is fully included within this supplementary guidance and the RUA tool. As mentioned, residual uncertainty assessment is mandatory for all new scheme appraisals. We are committed to developing our skills, knowledge and experience in this field. So one of the key issues around residual uncertainty assessment is who does what. From my experience as a technical modelling lead on appraisal projects, there was generally confusion as to who was responsible for reviewing and signing off an assessment. Realistically, it should be a team effort, with everyone bringing their knowledge and experience to the table. Within the supplementary guidance, we have provided a RACI matrix covering the key activities on who is responsible, who is accountable, and who should be consulted and informed at each stage. We've also provided a description of the key roles and what competencies they may require. Also, with improved reporting on RUA and the tool to bring together the assessment, the process for assuring or signing off an assessment should be an easier, more straightforward task. My final slide before I hand over to Phil covers sections 3 and 4 of the guidance. These sections give a step-by-step breakdown of the RUA process for each method, with details of what needs to be considered at each step. Phil will give a demonstration of this in a few minutes. As part of this, we have provided a number of uncertainty bounds for several variables that may be needed as part of your assessment. These uncertainty bounds have been identified through literature review and industry best practice to provide a guide to setting the small change test for the Tier 1 methodology or the wider sensitivity testing needed for the Tier 1.5 method. The example on screen is for Manning's, but the guidance covers much more than this, with uncertainty bounds including peak flow, weir coefficients, bridge afflux and more. To note, where industry standards have not been set for a particular variable, we provide a sensible suggestion of what the variable change should be. Finally, from me, I would like to acknowledge some areas of this field where we could or should provide uncertainty assessment, but we don't routinely at the moment. Some areas require more research for us to better understand the uncertainty for these environments, such as wave overtopping and aspects of natural flood management. Surface water systems are generally over-engineered to account for uncertainty, so there has been little need to consider them fully at this stage. And we also need a better understanding of uncertainty and our requirements in the flood mapping products. The soon-to-be-released National Flood Risk Assessment will start to consider this going forward, but we need to determine if and how that impacts our activities. Whilst not fully covered within an assessment or within the guidance, we do still provide details of these areas and where uncertainty may be present and you may need to consider. We'll obviously include them in the future as long as our kind of knowledge and experience increases in these areas. Okay, thank you, and I'll hand over to Phil for the next part of the presentation.
Cheers, Louise, that was great, thank you. So yeah, over the course of the next few minutes, I'd just like to talk you through application of RUA, and I'm going to talk you through application of RUA for one of the case studies, or actually 2 of the case studies from supplementary guidance. This is case studies 1A and 1B, so you can download these case studies and look at them following this webinar. A little bit of context, both these case studies are focused around the same flood risk management scheme, but it's the application of the Tier 1 and Tier 1.5 approaches to RUA respectively. This was a residual uncertainty assessment completed to support an outline business case. It was supporting a business case that was involving the development of linear defences to reduce fluvial flood risks to a community at risk on both the left and right bank of the channel. And as Louise says, it has been anonymised, but bonus points if you can actually spot where this is. Just for some context, these linear defences were in the range of about 1 to 1.5 metres high, and that was to provide a 50-year standard of protection. And it's that standard of protection that we're testing this RUA for. We calculated the RUA for a range of confidence intervals between 38% and 95%. And this was really to be able to properly understand that range of magnitudes of RUA to be able to then make an informed decision as to what level could be taken forward. Practically, in terms of about how you go about doing this residual uncertainty analysis and the sensitivity tests involved for it, able to use the existing model. The one caveat and one thing to be aware of is if you are doing it for linear defences, it's important that that model includes glass walls, or at least those defences are sufficiently high that the sensitivity tests don't result in overtopping of the defences. We want to understand what the resulting level is as a result of these sensitivity tests that we're doing for the RUA, so we mustn't have any overtopping. We've also calculated the residual uncertainty allowance for all the cross sections in the model, as that's easy and quick to do. But really, we're most interested in those ones that align with the linear defences that are visible on that screen. So let's move on a little bit. How do you go about applying this? The 5 key steps to applying residual uncertainty analysis. I'm going to just run through these briefly here, but over the following slides, we'll delve into a little bit more details on each step. So first step is we must identify the primary variable. In simple terms, the primary variable is the output from the model that we're most interested in and that informs the scheme design. So in the case of linear defences, the scenario that's probably most commonly dealt with, we're most interested in the water level output from that model. It's that water level that determines the ultimate height of the defences. And so in this case study and in many studies, the primary variable is going to be water level. We must then identify and screen the secondary variables. Now, what is a secondary variable? Well, a secondary variable in simple terms is just any variable or sort of input parameter into that model that we know has uncertainty associated with it, and we know that it has the potential to impact the primary variable. So for example, we know that Manning's N, there is uncertainty associated with the choice of that value, and we know that that does impact water level. So we must first identify all of the variables that have the potential to impact that primary water level, but then we must screen those, and that's an important step. And what we're doing in that screening exercise is to make sure that we retain the secondary variables that have the potential to notably impact that primary variable. So for example, we might identify that there's uncertainty in a weir coefficient within the model, but if that weir is nowhere near the study area and doesn't impact the water levels in the study area, then it would be reasonable to exclude it from the analysis. So we're essentially creating a subset of variables that we take forward to assess for residual uncertainty assessment. Step 3, we must define a confidence distribution to each of those secondary variables that we've taken forward. I would say this is probably the most difficult step, not because it's technically challenging, but it is relatively subjective at times. I'll touch upon this in a bit more detail, but it's just a case of doing the best effort at this. Use your sort of professional and pragmatic judgment with this one. Once you've defined those confidence distributions, we're essentially going to quantify the effect of each secondary variable on the primary variable. Simple terms, we're just doing a range of sensitivity tests, no different than we would normally do with modelling. And we do that for each secondary variable to understand that impact and that relationship. And from this, we can then calculate or estimate the overall residual uncertainty associated with that primary variable for each of the confidence intervals that we're interested in. So let's talk through each of those steps in a little bit more detail. I skipped over step 1 because there's not much to it, but as I've said, it's about defining the primary variable. This is a linear defense scheme. We're most interested in the water level from the model, so our primary variable is water level in this instance. We're then going to try and identify each of the secondary variables from this model. And for this case study, we've identified 6 primary variables. I won't go into the details of each one. I'm sure you can read on the screen, and there's more information in the case study. But a couple of things of note here. Firstly, when we're defining our secondary variables, it's important that each variable has independence. So you'll see that there's a number of sub-variables there that have been grouped under a single variable called fluvial peak flow estimates. I say it's important that they all have independence, and that's the reason that's been completed. Just want to pick out a couple of these variables that I think, from my experience, are commonly within a residual uncertainty analysis, and more than that, are commonly the greatest contributors to overall model uncertainty, and that is those fluvial peak flow estimates, so uncertainty in our hydrology. And uncertainty in our choice of Manning's N. It really does affect water level, and therefore it generally is a large contributor to the overall uncertainty allowance. A couple of things I'd like to point out: we screened a couple of variables out from this analysis. So we identified, for example, that there was uncertainty in the hydrograph volume. The reason we screened it out is because we know that this system is peak flow controlled. It's not volume sensitive. So whilst there's uncertainty in the hydrograph volume, this doesn't have the potential to notably impact the water level in the area of interest. Similarly, we screened out accuracy of channel representation because we're really confident on the representation in the model, so it's therefore not a notable contributor to the overall sort of uncertainty. And finally, we screened out blockage, and the reason for this is, whilst there's uncertainty associated with blockage, this is something that really should be dealt with through design and through mitigation in design. So say we've defined 6 variables that we're taking forward in the analysis, and we must then define the confidence distributions associated with each of these. I won't talk through each one of them again, but just picking out some sort of key points of note for this. Firstly, it's really important that if you're doing this, you try and have a look at and refer to section 3.4.3 of the supplementary guidance. We put a lot of time into trying to compile evidence and guidance from literature around confidence bounds for some of the sort of key variables that you'll come across. And where it's not available in literature, we try to present an approach for how you may go about defining that. So definitely lean on the literature that's available. Beyond this, as I say, this is a difficult step. It can be challenging, but it's about taking the sort of best professional judgment that you can on this. We're not looking for perfection. We're looking to try and understand the uncertainty of that model, and you use that to inform scheme design. It's about our best estimates. It's better to have something than nothing. So let's just talk through one example. So this is a bridge coefficient, and the uncertainty associated with a bridge coefficient. If you were to look at the supplementary guidance, it will highlight that there isn't, at least to our awareness, there is no literature around the uncertainty and the choice of a bridge coefficient value. So we need to take an alternative approach to this. The approach that we've put forward and we think is sensible and proportionate is that about a 10% change in that parameter value is equivalent to about 1 standard deviation of error, the 68% confidence interval. I think once you have that, you can then calculate the magnitudes of uncertainty for each of the other confidence intervals as well. And that's important. You'll need that in the analysis. So that's defining the confidence intervals. If we move forward, we're then looking at quantifying the effect of each of those secondary variables on the primary variable. And as I said, in simple terms, this is just sensitivity testing or enhanced sensitivity testing. This is where the tier 1 and tier 1.5 approaches differ slightly. For the tier 1 approach, you're going to make a small change to each secondary variable independently and look at what the impact of that is on the primary variable. And with that sensitivity test and with the baseline results, you can develop a relationship that you can extrapolate out and calculate the impact on the primary variable for any change or any degree of magnitude of change for that secondary variable. And this is the tier 1 approach. This is assumed to be a linear extrapolation. In terms of the tier 1.5 approach, this this is an enhanced approach, and what we're actually doing is we're testing the model with a magnitude of change that directly correspond to each of the confidence intervals of interest. And the figure on the right hand side of this shows the difference of those two approaches. This tier 1.5 approach is more robust in that estimate, and where possible, I really would encourage you to consider using the tier 1.5 approach. It is a few more simulations, but it is only a few more simulations, and it really does increase the robustness of it quite considerably. Just very quickly, if you are doing the tier 1 approach, where you're making that small change, maybe a question around what is a small change? Well, unfortunately, it's down to you as a practitioner to decide that, but it is just a small change. And think about small relative to that confidence distribution. Generally speaking, 5 to 10%, that sort of ballpark, but you will need to make a judgment around what is appropriate. So we've done the sensitivity tests. We can now calculate the residual uncertainty allowance. As Louise has mentioned, there's the supplementary guidance, and as part of the supplementary guidance, we've developed a tool to be able to support with the calculation of this. It's an Excel-based tool, and it provides functionality for calculation of RUA for both the tier 1 and the tier 1.5 approaches. It also allows you to do a hybrid approach. I won't get into this too much detail, but what it means is that you could assess all your secondary variables with a tier 1 approach, so the quicker method. Once you've identified the sort of greatest contributors to the overall uncertainty of the model, you can then enhance it with doing a tier 1.5 approach. So you might have 6 variables that you do under tier 1. 2 of those are greatest contributors. You could assess them with tier 1.5 and combine the results. Just another summary of some of the sort of functionality. It allows you to calculate up to 4 different confidence intervals. You can take forward 14 secondary variables for tier 1 and 6 secondary variables for tier 1.5. And it also allows you to summarize the results over a range of assessment locations. So in this case study, we want to look at a summary of the results across the nodes that correspond to each of the linear defenses. And finally, and I think this is brilliant, it is open source, so it's flexible and adaptable. If you need to change the way this tool is set up, or you need to add additional secondary variables, it is there for you to do that. The only caution I would say is just if you are starting a new project, try and pick up the original version of this, or just be absolutely sure that the version you're picking up is robust, obviously prone to error as you start to adapt it. So in terms of the results, what do you get? Well, through the tool, you get tabulated results. You get results for the method you've completed. And on here, I show the results from this case study for the tier 1 and tier 1.5 methods. As you'll see, hopefully you can see there's a small difference between these two approaches. And that's just that refinement through calculating the actual impact for each of the confidence intervals of interest. You can see that the results are summarized for both the left and the right bank. That's that result summary that I've just mentioned. I've also included on here a figure, and this is just a mock-up based on a project that another project that I'm working on. It's not accurate, but it just shows that if you've got the results for all of your cross sections, then you can sort of thematically map it to really sort of emphasize the areas where the greatest uncertainty is. And I think this will be really useful for scheme design and sort of informing sort of consideration of other mitigation measures, just being aware of those where that greatest uncertainty lies. So final slide from me before I hand back to Louise is how can Flood Modeller help with the calculation of it? Well, so there's really 2 things from an existing functionality perspective. There's the batch simulator, which is in the existing version of Flood Modeller. And it'll really help you to manage the simulations that are required for a residual uncertainty assessment, to monitor their progress and check they've completed without errors, etc. Also got the Flood Modeller API. For those of you who are not aware of it or don't know too much about it, this essentially allows you to programmatically interact with Flood Modeller and offers almost limitless flexibility. It would be possible to automate residual uncertainty assessment through the Flood Modeller API, and you could automate all of the steps if you wanted to. And then finally, in terms of future functionality, really excited about the up and coming release of Flood Modeller next year, Flood Platform next year. This will definitely add robustness and efficiency to completing the simulations that are required for RUA, but also we're looking at trying to include some tools around residual uncertainty analysis in there as well. Ultimately, my personal ambition would be that residual uncertainty analysis is something that's completed automatically for every project, and hopefully one day in a future release of Flood Platform we see that. So with that, I will hand back to Louise to talk through some of the reflections from the Supplementary Guidance project.
Thank you, Phil. So this slide looks at some of our reflections and known limitations around applying RUA and development we may need to consider in the future. So as mentioned previously, there are still areas where we require further knowledge and experience to kind of fully understand residual uncertainty and how we bring that into this guidance. And we're kind of keen to support further research in specific themes to help us to achieve that. The application of RUA is currently skewed towards new schemes, but we obviously have many assets that are existing and that need refurbing and rebuilding, and the role of RUA in these cases is not always well defined, so we require kind of more thought on how that is applied for those sorts of cases. Also, when we were undertaking the case studies, certainly for the storage example, it raised some questions around applying RUA to complex schemes. The case study leads to an answer that in practice is kind of unlikely to be technically or financially feasible, but the aim of RUA is not to block development of schemes. It's about understanding uncertainty within schemes, considering how we respond to that uncertainty. That may be through reducing the uncertainty in your data that you're using, it may be through adding freeboard, but it may also be through other mitigation of the risks. Residual uncertainty is no longer just about building defences bigger or deeper anymore, and there is kind of more flexibility in the options available. We have to make sure that we are proportionate in our response, which is a key principle in the 2017 guidance. And whilst this guidance is a great step forward, we acknowledge that there are still areas that we need further development. We don't expand on tier 2 methods within this guidance, as this kind of remains computationally difficult with the tools available currently, but this may be required in the future if more projects start to utilise this methodology more. To ensure RUA becomes more mainstream within our projects, we may want to consider how we build it into our project requirements, such as kind of revisiting the standards we set for sensitivity testing. And we'd also like to see how RUA can develop across the industry in terms of using API and software development, like Phil has just mentioned. So moving away from standalone spreadsheet tools. So finally, the suite of documents is now available to access via the Environment Agency. You can use the inquiries unit using the email address on screen, or if you're one of our framework suppliers, you can access through the modelling standards and guidance page. We're also developing a number of bite-sized training videos to support those working with residual uncertainty assessments for both those new to RUA and practitioners. And we're also considering a more in-depth practitioner session next year, and we'll be gauging the interest for that during the Q&A section. So that is our final slide.